um, he brings out very fundamental things in a very simple manner that most of us can understand. So I won't stand between you and Professor John Chalker. John, the, the podium is all yours. Please.
Okay, thank you very much, Rajesh, and good afternoon to everyone. So it's very nice to be speaking at this meeting, and actually for me it brings back some very pleasant memories of a visit that I made to Chennai about 5 years ago. Um, so what I want to do in this talk is discuss a way of thinking about a phase transition in disordered interacting many-body quantum systems, known as the many-body localization transition, a way of thinking about it that uses this space-time duality approach. So even if some of the physics background is not familiar to all of the participants, I hope the spirit of what I'm describing will fit with the meeting. So I should mention that what I'm talking about is joint work with Sam Garrett, who was a graduate student in Oxford and is now a postdoc at Berkeley. So here's the outline of what I want to talk about. I realize I should begin perhaps by saying a little bit about what's understood by many-body localization. So I'll attempt a one-slide introduction to that idea. And then I'll mention Flock A models, which quantum circuits for Flock A models, which I think are central to the ideas that are being talked about, and what I mean by the transfer matrix description, which is essentially switching in this space-time dual way. And then I'll talk about the consequences for the transfer matrix description of the many-body localization transition. And one of my main points will be that whereas the many-body localization transition is often said to be very different from the other examples of phase transitions that we know about, in this way of looking at things, it seems to be rather similar in the sense of having a type of symmetry breaking. And the final part of the talk will be to discuss how we can think about this symmetry breaking in terms of Feynman paths and what's known as the diagonal approximation. So to start, let me attempt to explain very briefly what's meant by this idea of many-body localization. And to discuss it, I'll use the language of Hamiltonians, even though I'll be phrasing things in terms of quantum circuits in the rest of the talk. So let me think about one-dimensional quantum spin system, which has sites on the lattice and spins represented by Pauli matrices in the usual way at each site. And suppose that we have some coupling between neighboring spins and also some randomness in the system, which is represented by these fields acting on the different sites with the strength and orientation of the field chosen from some random distribution. Then the belief is that the eigenstates of a system of this kind can be in one of two phases, depending on the strength of the coupling compared with the strength of the randomness. So if the randomness is weak, then it's natural to expect that a system of this kind would be ergodic at long times, and that's the many-body delocalized phase, if you like. On the other hand, if the randomness dominates and the coupling is weak, then the belief is that there's a quite different kind of phase, a many-body localized phase. And one way of specifying the features of this phase is to say that it has many local conservation laws. And to make that explicit, one can think of transforming this original Hamiltonian and rewriting it in terms of a new set of operators. So that's to say, replacing these spins sigma with some new spin-a-half operators denoted by tau. And the transformation between the two sets of operators should be a local transformation. And in this transformed Hamiltonian, the couplings are also expected to be local in the many-body localized phase. And the point is that because all of the operators in this transformed Hamiltonian commute, the eigenvalues of the TZs for each of these new degrees of freedom are conserved quantities. Okay, so it's that transition that I want to talk about, but through the prism of space-time duality. So the type of models that I'll be discussing involve, again, a lattice in space, and I'll think of a one-dimensional system. And on each side of this lattice, I have a spin or a qubit with some q-dimensional local Hilbert space. And I represent the time evolution using a quantum circuit. So at one stage of the time evolution in this type of quantum circuit, I couple neighboring pairs of spins with some unitary gate. And to have some kind of correspondence to the Hamiltonian system that I was talking about before, this time evolution will be periodic with the minimum possible period, which is what's drawn on the slide here. So that the model is a model for Floquet time evolution, periodic time evolution. So to specify a particular system, of course, I need to say how I choose these two-side gates, and I'll be thinking about random systems. And so what I'll actually be specifying is an ensemble of systems. But I'll explain the space-time duality content of what I want to talk about first, and then I'll come back to some specific examples of models and explain what those are later on. Okay, so the particular way that I want to characterize the physical properties of the systems I'm discussing is in terms of the eigenvalues of the evolution operator, which is simply the Floquet operator for the system for a single period, which I'm denoting by W here. So, of course, because the evolution operator is unitary, its eigenvalues are parameterized in terms of phases. And the simplest thing that we can consider is what's known as the spectral form factor, which is written in terms of phases in this way, and which is simply the Fourier transform with discrete time t as the Fourier transform variable of the 2-point distribution function of these eigenfaces. So this spectral form factor can be written in terms of the evolution operator. If I use this notation, the evolution operator after t time steps, w raised to the power t, is w with t as the argument, then the spectral form factor I can evaluate by taking the trace of w of t modulus squared. And then, as I mentioned, I'm always dealing with an ensemble of systems, and so I can think of an ensemble average, and I'll do that, and that's what I mean by the angular brackets. So it's useful to have in mind some toy examples of possible behaviors for the spectral form factor, and that's what I'd like to remind you of next. So we have two very simple possibilities. One is that the phases are completely uncorrelated. We have a Poisson distribution. And in that case, after averaging, the only terms that contribute to this sum are the diagonal ones. And so the value of the spectral form factor is simply the number of diagonal terms, which I'm denoting by n here, completely independent of this Fourier transform time variable denoted by t. We can get a completely different possibility if we imagine that W is a random unitary matrix that's distributed uniformly over the group. In other words, a matrix drawn from the circular unitary ensemble. And in that case, level repulsion suppresses the value of the spectral form factor at short times. And in fact, the spectral form factor is equal to t up to a time scale which is known as the Heisenberg time, which is essentially 1 over the level spacing, and then it's constant at longer times. So these two toy types of behavior are models for, in the first case, the MBL phase, and in the second case, the ergodic phase. And in point of fact, the kind of behavior that you get for the spectral form factor in those two phases is like this. So in a many-body localized system, the spectral form factor reaches its long time value after some time scale that's microscopic unless you're close to the transition, and in particular that's independent of the system size. Whereas in an ergodic phase, well, again, there's some different behavior at early times up to a time scale which you could call the Thouless time. But then there's a very wide time interval in large systems in which the spectral form factor looks as it does in random matrices. That's to say, it's linear in time. And when we make an analogy between some spatially extended quantum circuit and random matrices, then obviously one of the issues is how the size of the random matrix is related to the size of the system. And of course, we should choose the size of the matrix just to be the size of the Hilbert space. So if we have an L-site spinor-half system, then the size of the random matrix and the size of the Heisenberg time grows exponentially with the length of the chain. So what I want to think of now is, in a kind of outline way, what's involved in evaluating this spectral form factor, starting from one of the quantum circuit models that I had sketched near the beginning of the talk. And in a pictorial fashion, you can imagine the calculation of the spectral form factor, that's to say the modulus squared of the trace of the evolution operator over t time steps, as looking a bit like this. So I have space running horizontally, as in my previous pictures. And now, because I'm taking a trace of the evolution operator over t time steps, my time coordinate has become wrapped on the cylinder. And because I'm taking the modulus squared of the trace of the evolution operator, I have not one cylinder, but two. So if my drawing skills were better, then I would have filled in a whole lot of two-site quantum gates on the surfaces of these cylinders, but I hope you'll be able to imagine that they're there. Now, as I think we've heard, the idea of space-time duality is that we can evaluate something like this either by taking traces on a time slice, which is what we're doing when we think about the trace of the evolution operator, or alternatively, we can take traces on a space slice, and instead of moving around the cylinder in the time direction, we can move from left to right along the length of the cylinder in this picture. Those traces have different dimensions related to the length of the system if we're considering a time slice, or the size of the system around the circumference of the cylinder if we're thinking about the trace on a spatial slice. After averaging, this system is translationally invariant, and if the choice of disorder that I make at each slice is statistically independent of the disorder on the neighbors, then what I wind up with is a way of expressing the spectral form factor via the trace of a transfer matrix raised to a power that corresponds to the length of the system. So at this stage, this transfer matrix is very much like the kind of transfer matrix that you might deal with if you're considering a problem in statistical mechanics, such as, for example, the two-dimensional Ising model. And something that's very familiar in the treatment of transfer matrices in statistical mechanics is that if there's some symmetry breaking in the model that you're formulating in this way, then that symmetry breaking shows up in the spectrum of the transfer matrix. So there's a correspondence between broken symmetry and, in fact, degeneracy of the leading eigenvalues of the transfer matrix. So what I want to argue next is that from the behavior that I've already talked about of the spectral form factor in the two phases, we really should expect a degeneracy which changes at the transition and which suggests this kind of symmetry breaking. So let me explain how that works. So if we use this space-time duality approach and express the spectral form factor in terms of a spatial transfer matrix, and if we consider specifically a system with periodic boundary conditions in the spatial direction as well as periodic boundary conditions in the time direction as implied by the definition of the spectral form factor, then the spectral form factor we can write as sum over the eigenvalues of this transfer matrix, which I'm going to order in decreasing magnitude, with each eigenvalue raised to the power of the length of the system. So if we're in the ergodic phase and in this wide time window between the Thouless time and the Heisenberg time, then, as I said, the spectral form factor behaves as it does in random matrix theory. And for this model with, for a system at least without time reversal symmetry, then the spectral form factor is simply equal to the discrete time variable t. Now, to get that behavior from this expression in terms of eigenvalues, well, the striking thing is that the spectral form factor is independent of the length of the system. And so this power of L shouldn't appear in the results for the spectral form factor. And of course, the way that that can happen, in fact, I think the only way that it can happen is if the leading eigenvalues of the transfer matrix are simply unity. And at the same time, if the spectral form factor is going to be equal to t, then we need not just a single leading eigenvalue, but in fact, we need t of these eigenvalues to be degenerate, and then the lower ones to be smaller than 1, so that they don't contribute to this sum, at least when L is large. So in other words, there's exactly the kind of degeneracy in the leading eigenvalues here in the ergodic phase that one usually associates in a transfer matrix with a type of symmetry breaking. On the other hand, if we go to the many-body localized phase, then the behavior of the spectral form factor is simply that it's after some microscopic timescale, which I called t psi, the spectral form factor is essentially equal to the dimension of the Hilbert space, and with Q state a Q state Hilbert space on each side, that's simply Q to the power L. So to recover that from this expression for the spectral form factor in terms of eigenvalues of the transfer matrix, what we need is a leading eigenvalue that's equal to the dimension Q of the local Hilbert space, so that we have Q to the power L from the leading term here, and then the sub-leading eigenvalues should all be smaller. So that's the picture, that we've got a form of symmetry breaking when we go from the MBL phase to the ergodic phase. And in the rest of the talk, what I want to do is firstly to give you some evidence in support of this picture, and then secondly to give you an interpretation of the symmetry breaking in terms of Feynman paths. So as far as evidence goes, I want to talk about two models. There's one model involving weakly coupled sites at large Q, where we can get analytical results for the ergodic phase, and a second model which is essentially the kind of system that I used at the beginning to explain what I mean by many-body localization, where we've got numerical results. So the model that we can get analytical results for, we get the analytical results by taking the dimension of the local Hilbert space Q to be large, but we can formulate the model for a general value of Q. And again, the picture is that we want to specify a Floquet operator that takes us through one time step for a system that's defined on a lattice. And in the case of this model, we think of the evolution operator as having two factors. One factor involves doing a random rotation independently on each side. So these are Haar-random unitary matrices. And the second stage of the time evolution in one time step couples the sites together. And for simplicity, we take this second stage of time evolution to be diagonal in some site bases that we're working in with random phases on the diagonal. And these phases depend on the states of neighboring pairs of sites. So if these phases were all zero, there'd be no coupling between the sites. And if the phases are large and they fluctuate strongly from one state to another, then there's strong coupling between the sites. And if I take the phases to be random, then the mean square value of the phases gives me a coupling strength in the model. Okay, so it turns out that this model you can solve analytically at large Q, and you can also study it numerically for finite Q, provided Q is not too big. And the kind of phase diagram that you get for the system as a function of the coupling strength and the size of Q looks like this. We have an ergodic phase when the sites are strongly coupled, and an MBL phase when the sites are weakly coupled, and some phase boundary. And what we can do is solve the system in the large Q limit for some fixed value of epsilon, and actually derive properties at a fixed value of time. Because the phase boundary as Q gets large goes towards epsilon equals 0, that means that we can access the ergodic phase, but unfortunately not the MBL phase. So that gives us a way of studying the eigenvalues of the transfer matrix that I was talking about. And what we find in the ergodic phase is exactly the kind of degeneracy that I was describing. And in fact, we see how the degeneracy appears as we go to the long time limit. So we find that the leading T eigenvalues have this form. The largest eigenvalue is non-degenerate, and it's equal to unity with a correction that goes to 0 at long times. And then the next T minus 1 eigenvalues are degenerate and smaller, but again close to 1 with a correction that goes to 0 at long times. And the other eigenvalues of the transfer matrix, in fact, go to 0 in this large Q limit if we keep time fixed. So in other words, we have exactly the type of behavior I was talking about in the ergodic phase at long times. The other system that I'll talk about is kick field Heisenberg spin chain in this Floquet formulation. So we have a time evolution operator over one time step that involves coupling sites first over, say, the even nearest neighbor bonds, and then over the odd nearest neighbor bonds. And this coupling has two factors in it. One is a Heisenberg coupling between adjacent spins with some strength J, and the other is free evolution of the spins on each site in local fields which are chosen to be random in their strength and orientation. And as I claimed at the beginning of the talk, you can show numerically that a model like this has two phases if the coupling between spins is below some threshold value, then it's in an MBL phase. And if the coupling is above a threshold value, then it's in an ergodic or thermal phase. So a model like this we can only study numerically, and the idea is to extract the leading eigenvalues of the transfer matrix that I described. Because we understand quite a lot about the symmetry sectors of the transfer matrix, by imposing different boundary conditions, we can isolate different eigenvalues. I don't have time to describe the details, but in that way we can find the leading eigenvalue of this transfer matrix as a function of the size of the system around the circumference of the cylinder, that's to say in the time direction. And this is a plot of the leading eigenvalues with the different colors corresponding to different values of the strength of coupling between sites. So this parameter J in the model, and changing the strength of J, we can go from an MBL phase at small j to an ergodic phase at large J. And what you see is that at least at long times, there's a switch between the two types of behavior that I've described in the two phases. So in the MBL phase, the leading eigenvalue is 2. And if we go into the ergodic phase, then the leading eigenvalue is unity. And of course, if we're close to the transition, then there are some crossover effects, and one would have to go to very long t in order to see which phase the system is in. So this picture gives part of the results that I was claiming, but the other part of the result was to do with the degeneracy of the eigenvalues. And we can extract that numerically as well. And what I'm looking at here is the value of the spectral form factor, that's to say sum over all of the eigenvalues of the transfer matrix raised to the power L, divided by the leading one raised to that same power. So in other words, this ratio counts the number of eigenvalues that contribute to the spectral form factor. It counts the degeneracy of the leading eigenvalue. And again, we see the type of behavior that I was talking about. So in the MBL phase, in the curves that are marked in blue, the degeneracy is simply unity. Whereas if we go into the ergodic phase, the curves that are marked in red, then the degeneracy of the leading eigenvalue is t. So to reinforce the message, in the transfer matrix, you see at the transition this change in behavior between non-degenerate and degenerate eigenvalues that's familiar in statistical mechanics from transfer matrices that describe symmetry breaking phase transitions. And in the time I've got left, I want to talk about that symmetry breaking in terms of Feynman paths that contribute to the spectral form factor. So I'm slightly abusing terminology to use the name Feynman here. I'm not talking about paths in a classical phase space, but rather paths in Fock space. So if we think, first of all, about the quantum amplitude to go between an initial and a final state in this Floquet system over t time steps, then of course that has the usual expression in terms of the evolution operator raised to the power t, which we can break down in terms of products of matrix elements, and we can think of the sum that's involved in multiplying the matrices together as being sum over paths in Fock space. So just to emphasize the picture, if we go back to this representation of the quantum circuit, then at a given time slice in evaluating a contribution to this quantum amplitude, I need to specify the state of the system at all the sites in the system. And if we talk rather than, if we discuss rather than quantum amplitudes, instead probabilities, then we have products of two amplitudes, and we have a double sum over paths. And if I think of Fock space as represented by points in the plane of the slide and some initial and final state, then we want to sum over paths that contribute to A and to A star as represented here. And it's obvious that the diagonal terms in the sum are special in that they're necessarily positive, and there may be circumstances where the fluctuations, the off-diagonal terms are less important. And in fact, there are a number of situations where focusing on the diagonal terms is the right thing to do. And this is the basis for studying semi-classical dynamics in a way that's been applied to low-dimensional quantum systems in the past. It's also the basis for the theory of mesoscopics and disordered conductors, where diffusons and couperons are basically the diagonal terms in the sum. And then recently for many body quantum systems, it's been developed in various ways. So random quantum circuits are essentially systems that are designed so that these diagonal terms dominate the calculation of physical quantities. And in the Floquet context, there are two approaches from Tomasz Prozen's group, which in different ways generate systems where these diagonal terms are the dominant ones. And there's also work on many-body semi-classics, which really develops the semi-classical ideas that were first put forward for systems with a small number of degrees of freedom. So applying this to the spectral form factor, the point is that these diagonal terms needn't just involve interference between a path and its exact image. And in fact, when we think about the spectral form factor, we can represent paths as closed loops because we're taking the trace of the evolution operator, and we get constructive interference between pairs of paths, either if they are identical closed loops with the same starting point, or if the starting point is displaced by one time step or two time steps, or in general up to t time steps. And it's the coherent contributions of these successive terms that gives a spectral form factor that's linear in time at times before the Heisenberg time in random matrix theory. And in these many body systems, my argument is that it's the selection of one of these pairings that's the symmetry breaking in the ergodic phase that's signaled in the behavior of the transfer matrix that I talked about. But I realize that probably I've used up my time, so I guess that rather than talk in more detail about this pairing, I should probably hand back to Rajesh.
Thank you, John, for a very nice talk. I think the floor is now open for questions. So, if there are any questions, you can ask now.
Maybe I'll start. Yeah. Hi, John. Yeah, nice talk. My first question is about the model with the diagonal coupling. So, and large Q. So there the circuit is not dual unitary, but nevertheless you are able to make these conclusions, correct?
Yes. So yeah, none of the models I talk about are dual unitary. There's duality in the sense that we're switching space and time directions in the way we think about things, but as you say, without having a dual unitary model.
Yeah. But there was also a talk by Bruno Battini yesterday. Maybe he is here today as well on dual circuits. I assume that where one is also able to show the spectral form factor is as in the RMT. So my question is also about maybe you were going towards that. I don't know, but the COE form factor seems considerably more involved in some sense. So do you have a corresponding model where there is time reversal symmetry and you are able to derive the COE form factor?
No, not in work that I've done. So this first paper from the Ljubljana group is for kicked random field Ising model that has time reversal symmetry, and they show that they get the first two terms in an expansion of the spectral form factor, as you would expect from the COE. Now, probably it would be possible to make a weak coupling large Q model like the one that I described that was also solvable, but I haven't tried to do that.
Thank you.
Can I add a short comment on that? So for dual unitary circuits, you still can. So you can define a model that has time reversal symmetry, for which in the thermodynamic limit, you can show that the spectral form factor has the right behavior that you expect from COE, but in the thermodynamic limit, it's just 2T instead of T. On the technical level, so we did that for a specific example, which is a kicked Ising model, which is a dual unitary model with time reversal symmetry. To do it for a more generic class, I was mentioning this briefly yesterday. So you can prove that the problem reduces to solving some algebraic condition. And you have to show that the only solutions to that condition is given by I mean what you would expect, let's say. But this particular step we didn't do in general. So there is only this kick teasing example at the moment.
Okay, thanks.
Are there any further questions? If not, let's thank John for a fantastic talk.
I have a
Yes,
question.
please go ahead.
So for the kick field, I think like the kick field Heisenberg's spin chain you showed the phase diagram. So there was a cutoff in the thermal phase in the for the like the coupling J. It had an upper bound half. So is there any like further phase transition crossing when J is crossing half or something?
Yeah, well, it's just that because J appears in periodic functions, you need to you need to specify a range. I mean, if I take J to be too big, then I come back into the MBL phase. So I think I just set an upper bound here so as not to you know, wrap around the circle more than once. So it isn't that there's a third phase if I go to larger values of J than 1/2.
Thanks.
Okay. Thank you, John, for a very nice talk. So I think we should move on to the next talk, which is by Dr. Ryotaro Suzuki from the Free University of Berlin. So, Ryotaro, can we?
Haram, yes, I'm sharing my screen.
Yes, please.